So we wanted to continue the discussion about free electron, the free electron model in solids. So let me summarize. We are talking about the free electron. How shall I call it? Well, approximation. It's clearly an approximation, right? Because it's it's an approximation where essentially, let me summarize, we are neglecting, this is neglected, so we're only left with the kinetic part of the Hamiltonian. We argued that the solutions psi k of R are given by a periodic part. So this is the periodic part, the U in Bloch's theorem, times the phase that comes with Bloch's theorem. Okay, so the periodic part is not a generic U, but it's a specific function, and it's a plane wave with G being a reciprocal lattice vector. So this is the way we solve the problem. Actually, the problem had already been solved. I mean, we knew the solutions. We simply rewrote the solutions in a way that was compatible with Bloch's theorem. The reason we did that is because this allows us to plot the band structure of this system by fixing a k and working at different g's. You remember we made these plots of the band structure as a function of k for different values of the reciprocal lattice vector, at least in one dimension. We then discussed the problem in the case in which we have one electron per unit cell. You remember we argued that if we have one electron per unit cell, we're only going to fill the lower bottom of the parabola, of the lowest parabola. And in this case, we've evaluated the Fermi energy for 1 dimensions and for 2 dimensions. Actually, let me write them here. So I need you to tell me because I can't remember the. It's certainly n squared here for 1 dimensions, but the fact that there's certainly an h squared over m here. Is it a pi? Pi squared. 8. Good, thank you. Oh, here? Okay, thank you. And for 2 dimensions, there's an n. There is again h squared over m dimensionally. Pi? Pi. Great, thank you. So this is the 2-dimensional case. By the way, I invite you to double check in textbooks because I'm not so sure that we did everything properly. And now we want to do it for 3 dimensions, okay, just to complete our exercise. So in 3 dimensions, well, in 3 dimensions it's a bit difficult to show it graphically because in 1 dimension we have a single dimension for k and then the energy. In 2 dimensions we have a 2-dimensional reciprocal space with the Brillouin zone, which is a 2-dimensional object, and then we have the energy as the third coordinate. In 3 dimensions, E of k is defined in a 3-dimensional space, right? This is R3. Actually, the Brillouin zone is a 3-dimensional space. So how can I visualize it? I would have to visualize it in 4 dimensions, right? The 3 dimensions where the function is defined plus the 4th dimension of the. So don't ask me to do it. I'm not yet able to make plots in 4 dimensions, let alone in 3 dimensions. So let me just reason in terms of things that we discussed last time, okay? So the essential thing is that the energy is, for a free electron model, given by h squared over 2mk squared. Of course, if we have 1 electron per unit cell, and therefore we are restricted to the lowest parabola. And the question is simply where to stop here, where we're going to stop filling this parabola. And we know the prescription. The prescription is that we have to fill exactly 1/2 of the full Brillouin zone. But now we're in 3 dimensions. All right, so the volume, so now we're dealing with spheres. It's definitely a sphere because the energy is spherically symmetric around K, right? So the more we fill the parabola, the surface that contains the allowed values of K would be, of course, spherically symmetric, that therefore will be a sphere, right? So we only have to impose that the volume of this sphere, which is 4/3 kf cube, which is the area of the sphere, where kf is the maximum vector, the vector corresponding to the last occupied state, be equal to the 1/2 the size of the Brillouin zone. Now, we need to introduce a lattice here, because otherwise how can we measure the size of the Brillouin zone? So suppose we are dealing with a cubic lattice, just to give an example. In fact, the results, once again, will not depend on the lattice we've chosen. They cannot depend on the lattice we've chosen, once again, because at the end of the day, whatever result we find for a specific lattice, it must be possible to generalize that result. That result must apply for any lattice, because we know that the problem, in principle, the electrons don't know about the existence of a lattice. So we can do our calculations assuming that there is a lattice underneath, but at the end of the day, the results must be universal. So you can check, if you wish. You can check with another lattice, and you will find exactly the same results. So let me do it for a simple cubic lattice. The volume of the Brillouin zone for a simple cubic lattice is 2 pi, lovely. 2 pi over a cube, great. Excellent. All right, so, well, Kf is equal to 3 over 8 pi 2 pi over a cube, right? To the 1/3, obviously. So it's a to the 1/3 is 1/2, right? So it's 1/2 3 over pi to the 1/3 2 pi over a. Okay, so the Fermi energy in 3 dimensions. Let me write it here so that I can use the blackboard later on. Is going to be given by h squared over 2m kf squared. So it's 3 over pi 2/3 pi squared over a squared. And again, if we want to transform it into a density, we have 1 electron per cell. The cell is a squared, a to the cube in 3 dimensions. So this is a squared over 2m 3 pi 2/3 pi squared, and this is n to the 2/3, right? Because n is 1 over a cube. 1 electron per unit cell, a cube. So 1 over a squared is n to the 2/3. So you see the progression here from n squared to n to n to the 2/3. I'm sure you could have guessed that this was a 2/3, right? Based on what? You wouldn't be able to guess that there was a pi square, a 3 or 1, I mean, all these coefficients. But the fact that it was the n to the 2/3, you could have guessed. Why? Yes? It's n, and 1 is, well, why not n to the 0? I mean, if you follow the progression, square, 1, 2, 1, 0. oh, 2 over 2, okay, fine. But I mean, what is the reason why it is like that? Okay, it's a good argument. You say, this is 2 over 1, 2 over 2, and 2 over 3. Yeah, correct. 2 over n. But why is 2 over n? This is a good observation. It's certainly 2 over, sorry, n. 2 over the number of dimensions. But why is it so? I mean, these two constants have to remain there, right? Because they are in the, these are, I mean, universal constants. They're outside there. They will remain there. So what's left to transform these coefficients into an energy dimensionally is what? H squared over m, what's missing in order to turn it into an energy dimensionally? The kinetic energy is h squared over m delta square, right? So it's 1 over L squared. So the dimension that you need to recover an energy starting from h squared over m is 1 over L squared. Space to the minus 2. So whatever, I mean, with the let's say, forget about the constants. Dimensionally, if you want to put the density here, the density must appear in such a way that dimensionally this is 1 over a length to the square, to the second length squared. So in one dimension, the density is already 1 over L, so it just has to square it. In 2 dimensions, it's 1 over L squared, so you're done. You don't need to put any additional powers. And in 3 dimensions, the density is 1 over L to the third. And therefore, in order to turn it dimensional into 1 over L to the second, you need to take the 2/3 exponent. Is that clear? We're just dimensional considerations. If you want to construct an energy out of h squared over 2m, I don't see it looks like you're, you might remember, okay, let me go back. You remember the discussion we had about atomic units, one of our first, did we discuss atomic units? Not sure. Okay, sorry. That's a good time to discuss atomic units here. Atomic units. So let me digress for 5 minutes and discuss atomic units. Atomic units of, well, energy, anything, are extremely useful in atomic physics, but as a consequence, they're also very useful also in solid-state physics, because the dimensions, the scales of energy, length, and everything that we are dealing with in solid-state physics are essentially those of atomic physics. So it's very useful to introduce atomic units. Now, how do we introduce atomic units? Well, the most obvious way to introduce atomic units is to start introducing at least one quantity which comes out naturally from the Hamiltonian. So you have an Hamiltonian, and the Hamiltonian is, let me for the time being forget about constants, factors. I'm just discussing dimensions here. So we have an Hamiltonian which is composed of a kinetic energy term, right? So h squared over m, and then there is a delta square. So whatever natural length we have, there will be, that length will be taken to the square. If the extension of the wave function, if this is a sine wave function, right, this will be the period of the sine wave function. If it is an exponential function, it will be the decay constant of the exponential function, whatever, okay? You take the delta square, what you get is the 1 over the typical size of the wave function. Is that clear to everyone? If I take delta square of a cosine of a sine, I get, if I have sine of, say, 2 pi over a x, right, which is a sinusoidal function with period a, I take delta square of this, and I get minus 2 pi over a squared sine of 2 pi over x, right? So what I get out of it is something that scales like the characteristic length of the wave function. Same, of course, forgetting about factors, numerical factors. Same with the exponential. If I have e to the minus e to the minus lambda x. Actually, let me put it like this, x over d, where d is the characteristic decay length of this exponential. I take delta square, and I get 1 over d squared, e to the minus x d, right? So what comes out is always the typical extension of the wave function. So kinetic energy dimensionally gives me something of the order of h squared over m, 1 over the typical dimension of my problem. And here I have to be careful, because now I have to, the kinetic energy term is universal. Every Hamiltonian has, non-relativistic Hamiltonian at least, has this as the kinetic energy. The question, of course, is what is the scale of the potential energy? And in atomic physics, the scale of the potential is given by E squared over a length, once again, right? But that's also true, sorry, I'm using characters which look very similar, sorry about that. This is L, like that. This is. So the Coulomb interaction is something that scales like 1 over L. This is, by the way, true also in the solid state, because in the solid state we know that the solutions are some combinations of solutions of atomic problem. Again, I'm not talking about the real factors, 2 pi, 4 pi, pi squared, whatever. I'm just talking about universal dimensions of the problem. Okay, so we have a kinetic energy that behaves like that if L is the typical scale of the problem, and the Coulomb potential which scales like this, where L is the typical size of the problem. Well, it is actually a general statement. The fact that if you have an Hamiltonian, the energy is going to somehow equipartition between the two parts of the Hamiltonian. Equipartition is a classical concept, but there are, you can actually show that, generally speaking, with the exception, of course, of just numerical factors, the energy is divided between the different terms of the Hamiltonian in a rather equivalent way, at least if you have kinetic and potential energy, right? You certainly have in mind the harmonic oscillator, where the kinetic energy is exactly identical to the potential energy. For the Coulomb potential, it's slightly different. The kinetic energy is typically 1/2 of the Coulomb potential. You might remember from atomic physics, right? The potential. So, the potential, typically, with exception of numerical factors, you typically get that the two contributions are more or less the same size. Now, this, of course, allows us to introduce an important scale of, a natural scale of length for our problem. What we need to do, essentially, is to say, well, let's choose the scale of length as our natural scale of length, the scale of length that makes these two terms equal, right? So let me introduce a scale of length such that this is equal to E squared over L. These are two energies, right? The kinetic energy, potential energy, so I can equate the two terms. Let me define, actually this is a definition. Let me define L in such a way that these two terms are equal. It's, for me, a good way to introduce a natural scale of length. Whatever comes out of this will be a typical length of the problem, right? And of course, L, if I do this exercise, will become h squared over E squared m. I'm sure you have seen this, right? This constant. What is this? The Bohr radius. In fact, it's the natural scale of length for the hydrogen problem, which is exactly given by this Hamiltonian. Okay? But to some extent, in the Bohr radius, there's more than just the hydrogen problem, because it's really something natural for whatever Hamiltonian contains kinetic energy plus Coulomb energy. Then, of course, the different Hamiltonians will differ in the numerical factors. But they will all share the same scale of length, which is the Bohr radius, factor of 2 or pi or whatever. So it's very natural for us to introduce this as a scale of length. Similarly, we can introduce a natural scale of energy. Again, this natural scale of length was such that these two terms were equal, so I can take either this or this, and they must be the same, of course, as the natural scale of energy. Okay, so I can introduce an energy which I call Hartree. One Hartree is E squared over the Bohr radius. Or equivalently, and I know they must be equal, H squared over M Bohr radius squared. Right? They must take the same value, by the way, because I define H Bohr precisely as the quantity that makes these two quantities equal. Now, we can also put some numbers here, and I guess you all know that the Bohr radius is 0.29177 blah, blah, blah angstroms, right? It's approximately 1/2 of an angstrom if you put the correct values for these universal constants. In fact, it is, right, a natural length. It's the length of the extension of the 1s orbital. It is also, within some numerical factor, the typical distances between atoms in solids, right? Atoms in solid are not meters far away. They're not picometers far away. They are roughly angstroms far away. That's naturally a consequence of the fact that the Hamiltonian that governs the behavior of atoms in solids is an Hamiltonian that is made of a kinetic energy term and a Coulomb part. And therefore, the natural scale of length is in the angstrom range, must be in the angstrom range. What about energies? The energy here is this energy, if you put inside, if you use the correct numbers here, is 27.21 blah, blah, blah electron volts. I'm using electron volts because electron volts, I guess, are probably the most natural unit of energy in physics. I would say it's even more natural than joules and other. Joules is okay for macroscopic systems, but for microscopic objects, the electron volt is probably the most natural unit. So the Hartree, in fact, is not so far from the electron volt. It's 27 times the electron volt. And of course, the binding energy of the hydrogen, of the 1s state of the hydrogen problem, is exactly 1/2 of the Hartree, right? It's called Rydberg. So one Rydberg is, in fact, one Rydberg is e to the e squared over 2 Bohr radius. So this is 1/2 of a Hartree. I've introduced all these units because, there's way more than we can say about these units and the connection with our problem here. For example, we may decide to express densities using Bohr radii. And it's quite frequent in the literature to find densities expressed in Bohr radii. If you do that, then this becomes a dimensionless number because it's the number of atoms, number of electrons per Bohr radius to the third. So it's a dimensionless number. But of course, you need to extract out the Bohr radius here to the 2/3. To the second. So there will be a number of constants here that will. In other words, you can write the Fermi energy in terms of h squared over m 1 over Bohr radius squared. And then you can extract the Bohr radius out of that. And everything becomes dimensionless, or everything becomes expressible in terms of Hartrees and Bohr radii. So everything becomes dimensionless in principle if you use those particular units. I don't want to go to this exercise because it's a bit tedious. I don't want to add more mathematics into this. But I just want you to keep in mind that there are some natural scales in the problem that we can use to express our quantities in dimensionless terms, assuming that the scale of energy and of length are given by these natural units there. If we replace those natural units everything becomes much more natural, and we assume that we are expressing everything in those natural units. Why did I say this? Oh, yes. In fact, the reason why I mentioned this is because I wanted to emphasize the fact that the kinetic energy dimensionally, I would like you to keep in mind the fact that the energy in general, or the kinetic energy in particular, can be written in terms of h squared over m times something which is the inverse of a length squared. I mean, that's something I would like you to keep in mind. Or, if you wish, you can express it in terms of the Coulomb, that is E squared over L. This is also dimensionally an energy, so you can use either this or this, depending on what is the constants that you have. For example, here we have h squared over m, so the rest must be 1 over L squared. Okay? So if you have a density, the density is 1 over L to the cube, and therefore to transform it into 1 over L to the second, you need to take the 2/3. Of course, all the numerical constants, the numerical factors, do not appear in a dimensional analysis. They are the result of a real calculation. Okay. What else? I think this is more or less all I wanted to say about the free electron approximation. With all this background information, those of you who want to know more about the free electron approximation can just open the textbook, and you'll find it quite easy to then follow more, elaborated concepts in this, for this regard, for what concerns this particular approximation. I need to move forward now and to go one step beyond the free electron approximation. Any question about the free electron approximation? Yes. Yes. Right. So it's the one that we derived for. We actually derived it for 1 electron per unit cell and for a simple cubic lattice. However, as we already discussed, we know that the Hamiltonian does not know about the existence of an underlying potential. So whatever result we obtain, that result must be more general than the specific case that we use to obtain it. Okay? This is just because we forced our solutions to, we manipulated our solutions to adapt them to the existence of an underlying solid. But if you start from here, nowhere, in principle, the electrons know about the existence of an underlying lattice. So the final result cannot depend on the lattice we used to obtain it. Okay? Since we didn't make an approximation in deriving this, right? Starting from here, all the way to this result, we didn't make any single approximation. Everything was exact. Okay? So if you do it for another lattice, for an FCC, for example, and for 3 electrons per unit cell, the result must be the same. If not, there is a mistake somewhere. Okay? So we obtain the result in a specific case of 1 electron per cell in a supercubic lattice, but it must be possible to generalize the result because the starting statement, the starting assumptions, did not know anything about the existence of an underlying. We introduced the lattice ourselves in order to carry out the calculation, and we didn't do any approximation.
Now, in this dimension, you said that what can we say about the Fermi vector in 3 dimensions?
Okay, so what can we say about the Fermi vector in 3 dimensions? It was here.
Because we know that it's a sphere.
It's a sphere. So the Fermi surface, okay, I didn't mention what the Fermi surface is. The Fermi surface is the set of points that correspond to the highest occupied electronic orbitals in our problem. So that's a sphere, yes.
It means we have many Fermi vectors.
Sure, it's a sphere. So we have what we obtain is the radius of this sphere. Okay, so it's a sphere. So the set of points corresponding to the energy states, the electronic states with the highest possible energy, in fact, the Fermi energy, are located in a sphere, right? Because as soon as you fill your parabola, you're going to fill states which are all the same distance from the origin, because the same distance from the origin means the same kf, and same kf means same kf squared, and same kf squared means same energy. Okay? So yes, the Fermi surface, we didn't introduce the concept of Fermi surface, but Fermi surface is, thank you for pointing out this, the Fermi surface is a set of points corresponding to electronic states that are at a Fermi energy. Sorry? So it's the set of points corresponding to electronic states that are located at the Fermi energy. So for the one-dimensional system we had before, K, F, if Fermi energy was here, this is a point, this is the Fermi surface, 2 points. Okay, these are the 2 states that have the Fermi energy, and this is 2 points. In 2 dimensions, it's actually a circle, because we know that if we have our parabola and we take the Fermi energy, that is, we take all the states at a given energy, at a given height, right? This corresponds, in the plane, it corresponds to a circle. So the Fermi surface, a set of points, k points, that correspond to electronic states which are at the Fermi energy, is a circle. In 3 dimensions, well, you have to now imagine work in 4 dimensions. So essentially it's a set of points that are located at the same distance from the origin, because same distance means same k squared, and same k squared means same energy. So in 3 dimensions it is a sphere. And the states that are filled are the ones that are contained within that sphere. Of course, in the free electron approximation. Yes?
I thought you want to say something about the degeneracies and Fermi energy.
There's not too much I can say at this point. I'm going to say something in a minute about this degeneracy in particular. But this degeneracy, well, there may be a few things that I could say, but it's nothing really important. But yes, I mean, you're right. This is a degeneracy. I mean, all these states are indeed degenerate. They have the same energy after all. But there's nothing special I can say about it. Let's say simple. There are a number of more complicated and things that I could say about it, but it would be too much for you. Okay, any more questions? Yes?
Since we discussed the nature of the materials like insulators and
Yes.
for the characteristic gap also,
Yes.
so it's a good approximation to describe a superconductor with the free electron number, or
Okay, so your question, we've already discussed metals and insulators in terms of whether there is a gap or not in the band structure. Your question is whether these kind of models can be used to describe superconductors. This is your question. Okay, now, the first thing I have to say is that in order to describe superconductivity as a phenomenon, as a physical phenomenon, we need to go well beyond this particular description. There is an important reason why, among others, why this is the case. And this is the fact that superconductivity arises because of the interaction of electrons between each other. And also because of the interaction, particularly in the BCS standard picture of superconductivity, because of the interaction of electrons with the underlying lattice. The theory that we have constructed so far, for once, I mean, it does not contain electron-electron interactions, for example. We have completely neglected the electron-electron interactions. So there's no way we can understand superconductivity based on these considerations. Although, however, what I can say is that there are theories like the BCS theory, Bardeen-Cooper-Schiffer theory of superconductivity, which use band structures as a starting point to then add up electron-electron interactions and interactions of the electrons with the lattice. Okay? So although this particular theory does not contain superconductivity alone, it is an excellent starting point to then add up the elements that are missing and understand superconductivity. Okay? So in a superconductor, certainly you need to start from a metal at the level of band structure. So you need to start with a metal, so this is a good starting point. I mean, this free electron model could be a good starting point for the description of superconductivity, but then you have to introduce other elements which are clearly missing here. And in fact, at the end of the day, I don't know how many of you are familiar with superconductivity, but at the end of the day, you actually come out with a system with a finite gap. But that gap arises from the interaction of the electrons with themselves and the interaction of electrons with the lattice. Yet the starting point, if you want to describe that particular physics and that gap, is a system which can look like this one. Why not? Yes?
I want to know if the number of the field states is related to the number of electrons we have.
Of course. The number of field states is 1/2 the number of electrons that we have available, right? Because each state contains 2 electrons. So the number of states must be exactly 1/2 the number of electrons we have. Of course, here we are neglecting magnetism. We are neglecting the fact that spins can be different. Let's assume that spins don't play a role, so that each electronic state can be filled with spin up and spin down. So by definition, the number of field states must be equal to 1/2 the number of electrons that we have. The problem, and we already discussed this, is that unfortunately, here we have a continuum of states, so an infinite number of states and an infinite number of electrons, so we need to count them properly. The fact that one is 1/2 of the other one, no question about it. The problem is that they're both infinities. So we need to play with those infinities. And the solution we came out with a few lectures ago was that we concluded that this infinite number of states we know can accommodate the equivalent of 2 electrons per cell, which is, of course, an infinite number of electrons because a crystal is infinitely large. But at least we can count them per unit cell. Okay? So we know that all this continuum of states, infinitely many, we know that this corresponds to infinitely many electrons, but in a very precise way, corresponding to 2 electrons per cell.
So
Okay?
the number of the electrons that can accommodate, of the number of the states, I think should be, because I don't know, but I saw somewhere they're saying it is the number of the primitive cells you have in the crystal.
In some sense, yes, it's correct. Because I'm saying that here I can accommodate the equivalent of 2 electrons per cell, right? But because each one of these states contains 2 electrons, right? You're right. The number of states is equal to the number of cells, of the unit cells. Yes, that's correct. It's actually the same. It's actually the same statement. What I'm saying is that the total number of states here, which is infinity, is such that I can fill, if I fill it completely, I can do it with 2 electrons per cell. But because in each state I can put 2 electrons, that means that the total number of states I have here is equal to the number of cells. They're both infinities, but they're equal. They're equal infinities, exactly equal. Yeah, so you're right. It's an exactly equivalent statement, if you think about it, right? I'm just saying the same. I'm saying that I can fill this infinitely many states with 2 electrons per cell. Any more questions before I move on? Okay. So, I think I can... what I'm going to do now is to move a little bit further and say, instead of having a pure free electron approximation, let me introduce a weak, small, perturbatively small potential. Okay, so I'm now going to introduce the so-called quasi-free electron model. Approximation. quasi because my Hamiltonian now is still kinetic energy. And then there is a potential here which is weak. We'll come back to what we mean by weak, how weak the potential must be in order for this approximation to work. In some sense, it is clear from what we want to be the starting point. This potential must be very weak compared to the kinetic energy of our system. But we'll see it later on, what we actually mean by that. In some sense, what we want to do in practice is to say, okay, let's assume that this can be treated as a perturbation on top of a problem that we already solved, which is the free electron problem. So now we're going to use perturbation theory. We're going to assume that the solution of the free electron problem is known. Well, actually, it's not an assumption. We've done it, right? We've solved the problem. And then we're going to add on top of this unperturbed solution, we're going to add a small perturbation. A small perturbation which goes in the direction of introducing the presence of an underlying lattice for the electrons. Okay, so if we have, for example, we deal with a one-dimensional system where the atoms are placed at some distance, a from one another. So far, we have assumed that the potential, well, felt by the electron was just a constant. Let me call it V0, right? Or 0, whatever, constant. This was our approximation here. I'm putting a constant because I want to mess up with the position of the atom. It's a constant. I can change this into an arbitrary constant if I wish, right? It's not relevant. I'm just moving it away from the position of the atoms, otherwise the plot is confusing. So far, this was the free electron approximation. The potential was a constant. And we said, well, the electrons don't even know about the existence of atoms if the potential is like this. There's no reason why they should see it. I mean, they don't see the presence of an underlying lattice. Now, what we're going to do now is to introduce a small perturbation that takes into account the fact that here there are atoms. So what is the simplest form of this small perturbing potential? Certainly it's something that must be attractive close to the nuclei, right? Because this is where the Coulomb potential is attracting the electrons. So let me draw a potential that is very simple and that mimics the presence of a lattice, right? It is a bit deeper in correspondence to the position of the nuclei, right? So it's somehow a first correction to the fact that the electrons must see at the positions where the nuclei are a little bit of attraction. And I make my potential very simple so that I can make my theory very simple. So I'm going to add to V0 a potential which is V bar cosine, in this particular case, of 2 pi over A x. This pink line. In fact, if I place the atoms here at the origin, let me actually put a minus here because I want the potential to be attractive where the atoms are. So for x equals to 0, A, 2A, 3A, 4A, the cosine becomes 1, and I want to make it negative at those positions, okay? So I put a minus in front. Well, assuming, of course, that V bar is positive. It would not be physically correct to say that this is a plus, right? Because otherwise I'm repelling the electrons from where the nuclei are. So from a physical point of view, this must be a minus. And I'm going to treat this as a perturbation on top of the solution that we already obtained for the free electron problem. Okay, so in perturbation theory, we have that this is the unperturbed solution, and this is the perturbation that we are going to apply. Now, a bit of refresh of what perturbation theory is. I assume that you are all familiar with perturbation theory. But let me just recall some basic concepts of perturbation theory before I move on and do the actual calculations. Perturbation theory in quantum mechanics, well, first of all, you typically distinguish two cases. You distinguish perturbation theory for non-degenerate states and perturbation theory for degenerate states. Are you all familiar with this? Yes, perfect. Perturbation theory for non-degenerate states. That's quite simple. Perturbation theory for non-degenerate states, what you have to do is simply take the expectation value of the perturbing potential with respect to your eigenvalues, at least to first order in perturbation theory. And that's the correction you have to add to your, so if we have perturbation theory for non-degenerate states, what I have to do, and the perturbation, so the Hamiltonian is H equals to H0 plus delta V. Delta V is the perturbation. For non-degenerate states, what I need to do is simply take the expectation value, at least to first order, over the unperturbed solutions, and this gives me a perturbation, a perturbation energy is simply the expectation value over the perturbing potential, at least to first order in perturbation theory. Well, to first order in delta V. I can go to second order in delta V, and I have to then construct my corrections by summing over all the states. You remember delta V squared divided by the difference between the unperturbed eigenvalues and blah, 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 blah. So that's theory, perturbation theory, non-degenerate states. For degenerate states, it's a bit more complicated, because for degenerate states, if you are within the manifold, a degenerate manifold, 2, 3, 4, n degenerate states, that is states with the same energy, it's not enough to just apply this rule, but you have to construct a matrix of delta V with all the wave functions that are inside that degenerate manifold. And then you have to diagonalize the corresponding 2 by 2, 3 by 3, n by n matrix. All familiar with this? If not, go back to your quantum mechanics textbooks or your lecture notes and try to find out where these statements are made, okay? So here you need to diagonalize an n by n matrix made of psi 0. Now I have to put an index, of course, delta V psi 0 j, where these are degenerate states. You take all the states in the degeneracy in a manifold within a given degenerate manifold, so all states within the same energy. You construct the matrix of delta V with all the states. It's a finite matrix. It's n by n, n being the dimension of the degenerate manifold. And you diagonalize it. And you get the eigenvalues and eigenfunctions after the perturbation. To first order, of course. That's still to first order in perturbation theory. Second order, well, you proceed more or less like in perturbation theory for non-degenerate states. You have to construct your sum over all the states, delta V squared over the eigenvalues. I don't want to discuss that. I mean, that's something, it's actually not relevant for our discussion. The relevant part for our discussion is the difference between degenerate states and non-degenerate states. Actually, if you think about it, the two cases are actually the same, because you can always say that if it's non-degenerate, the degenerate manifold has dimension 1, right? So you don't have to diagonalize anything, you just calculate that expectation value. It's a 1-by-1 matrix that you have to diagonalize. So it's actually, the two statements are not really different, they are the same statement. I'm just making a distinction here because the mathematical procedure is slightly different, but you can actually claim that this is just a particular case of this statement here. All right, good. If you're not familiar or if you don't feel confident, go back to your textbooks and try to refresh your ideas about perturbation theory. Okay, now, first clarification. Second clarification, okay, I'll have to use this side of the blackboard. Let's discuss the problem in 1 dimensions, okay? So we have this. If I introduce a perturbation like this one, this perturbation has the periodicity of the lattice. So Bloch's theorem is going to be still valid. The fact that we introduce a perturbation has not violated Bloch's theorem, because the perturbation we are adding has the periodicity of the lattice. So Bloch's theorem continues to be valid. We have this A, so the Brillouin zone continues to be the same. What's going to change, of course, is the eigenvalues of the problem. But the structure and the fact that we can classify states according to a given k remains valid, because this potential does not violate Bloch's theorem for that periodicity. What this implies is that when I play perturbation theory, I can do it within a given k. I can choose a k and say, well, let me now apply perturbation theory for that particular k. K continues to be a good quantum number. So I don't need to consider mixing between different k's, because what I'm introducing continues to satisfy my translational symmetry. So it's not going to mix states with different translational symmetry. I can stick to my quantum number k and work within that particular quantum number. Okay? It's a bit like when you do for the hydrogen atom, you introduce a perturbation which is spherical. You're not going to move away from the traditional quantum numbers. You do perturbation theory within the principal quantum numbers. The quantum numbers, sorry, within the quantum numbers that are a consequence of spherical symmetry, that is the angular momentum. So same here. So here we continue to work for a well-defined k. So our statements about different ways to apply perturbation theory will have to be made within every single k. So say we are here, which kind of perturbation theory do we need to use here? Well, the first one, perturbation theory for non-degenerate states. There's no degeneracy here. There's a state here, a state here, a state up there, there's no degeneracy. The tricky points, of course, are this one and this one. This is, of course, the same as this, right? Because it's periodical. So the only tricky points are k equals to 0 and k equals to pi over a, because here we do have a degeneracy. And here we do have a degeneracy. So here we have to be careful. We need to apply perturbation theory for degenerate states. So depending on where we are in the band structure, there will be two different approaches that we will have to use in order to understand the consequences of this perturbing potential on our band structure. So this is given. I don't need to keep it there on the blackboard. assume you're all familiar with this. So here I have to, let me do first the simplest case, this one, okay? I am here, and I want to know the consequences of how much is my energy here going to be changed, this one, for example, if I switch on a small perturbing potential. Yes. So therefore, I have to calculate psi k delta V psi k, where psi k is given by this function, and if we are there, psi k is equal to what? To the g corresponding to that particular state is, what is the g vector corresponding to this state here? We know that this state can be expressed in this way. What is the g corresponding to that particular state? The reciprocal lattice vector. Remember last time we classified the states according to their g vector for a given k. This one was g equals to 0. Right? This is just e to the I k r. It's the first parabola. This is the parabola with with g equals to minus 2 pi over a. This is the parabola with g equals to plus pi 2 pi over a. This portion of parabola is the one with g equals to 0. All right? So that particular state here has g equals to 0, 1. If you look at your notes, you'll find it. So this is actually 1. Well, let me put explicitly 1 because it's g equals to 0 times e to the I k r. This is this particular state here. Now, it's a right moment to start discussing about normalization. You remember that at some point I told you that we would be discussing normalization later on. Now, unfortunately or fortunately, it's time that we do it. Because if I don't discuss the normalization, how can I then calculate these expectation values if I don't know what is the normalization of the wave function? So I need to discuss the normalization of my wave functions. So how am I going to normalize wave functions properly? Well, you remember, in general, okay? Now let me actually go back to Bloch's theorem in principle, because, okay, let me open a digression here. How do I normalize states, Bloch states? Well, we began the discussion a few lectures ago, right? We said, well, certainly we cannot do it over the whole space. We cannot take integrals over the whole space, because over the whole space this is periodic, and therefore it's never going to go to 0. It's going to diverge. So we need to limit our integration over some finite but large region of space, for example. This is what you do in particle physics, for example, right? In particle physics, typically you say, well, let me normalize wave functions in such a way that I'm dealing with a very large, arbitrarily large region of space, and let me use that volume as the normalization of my wave functions. Well, this is a possibility. For solids, there's actually something even simpler than that, for solids, for periodic systems. I can say, why don't I normalize my wave functions within the unit cell? There is a natural region of space which I can use to carry out my integrals. Well, the point, of course, is that if I do that in the unit cell, I need to make sure that the integral is the same if I move from one unit cell to another one. It might not be the same. But in case of wave functions, if I take the square modulus of the wave function, which is what I need to do the normalizations, this phase disappears. So the square of the wave function of a solid, of a crystal, is a periodic function. The wave function itself is not periodic because of this phase. U would be periodic, but this phase kills periodicity. So wave functions are not necessarily periodic. However, as soon as I take the square modulus of a wave function, I get something which is periodic. And this is a very general statement, just follows directly from Bloch's theorem. So if you believe in Bloch's theorem, or if you prove Bloch's theorem, this is a natural consequence of Bloch's theorem. The square modulus of a wave function is periodic. Okay, now this is very helpful for us at this point, because we can really say, let's do all our normalizations within the unit cell. So let's say that our integrals are defined within the unit cell, and if we go outside the unit cell, we're just going to get exactly the same result. So we have a finite region of space which you can use to normalize all the quantities we need when we perform these expectations, these calculations, these practical calculations. Okay? So I'm going to assume now that the wave functions are, if integrated over the unit cell, psi k this is 1 over the unit cell. So this is the assumption I'm going to use, the definition, if you wish, of normalization for Bloch states. I want them to be normalized within the unit cell. UC here, notice, UC, unit cell. So I don't need to carry out integrals over the whole space or over infinitely large, arbitrarily large but finite regions of space like you do in particle physics. Let me just do it within the unit cell. I know that if I do it within the unit cell, that integral has to be the same throughout my crystal, and so why not just choosing the unit cell as the natural region of space where I normalize my wave functions? It's my choice. Remember, when you take these expectation values, the understanding is always that you divide by psi k squared, right? So in some sense, the criterion you use to normalize your wave functions should not affect the calculation of expectation values. The only thing you want to make sure of is that these integrals can be carried out, right? That they are properly normalized, normals, not divergent integrals. As soon as you manage to make them non-divergent, then any choice is fine, because then you're always dividing by psi k when you calculate an expectation value. All right, so the consequence of this for our plane waves is that the obvious normalization for a plane wave is simply 1 over the volume of the unit cell square root, right? Because this is, the square modulus of this is 1 of our free electrons. So the integral over 1, an integral of 1 over the unit cell is the volume of the unit cell, right? So the obvious normalization for Bloch states, in fact, is well, for plane waves at least, is just 1 over the square root of the volume of the unit cell. But more generally, I can impose normalizations by imposing the wave functions that normalize within the unit cell in solid state theory. So this statement is completely general. This statement is specific to plane waves, the normalization 1 over V. Okay, so now I need to remember that here I have 1 over V. Well, V is the Actually, sorry, let me call it omega because I don't want to confuse it with the potential. Just notation, sorry about that. By omega, I mean the volume of the unit cell. All right? So I wanted to calculate this expectation value. Where shall I do it? I do it here. So this is now the integral over the unit cell. That's my definition of expectation values. I can do it in the unit cell of 1 over square root of omega e to the minus ikr psi k star delta v minus v bar cosine 2 pi over a x times e to the I k r. We are in one dimension, so this is dr. Over the unit cell, that means between 0 and a. Right? The meaning of unit cell means between 0 and a in one dimension. Oh, I'm using, sorry. I'm using x here, but I mean r, of course. Okay? So I'm left with the integral of the cosine over a period. Whatever. What is the integral of a cosine over a period? 0, right? The integral of a sinusoidal function over the period of the oscillation must be 0. So, first conclusion. To first order, at least in perturbation theory, this state is not going to be affected by our perturbation. Second order, of course, it will be affected. But to first order is not going to be affected. Yes?
Why not we consider, okay, if we restrict or something that in the natural state, why don't we approximate like we have a potential wheel, and then we have an electron, okay?
Yes?
I don't know. I think we can make it like that. I don't know.
Okay, let me, your question is whether, since we're restricting our choice to the unit cell, why don't we put everything into infinite walls?
No, I mean, no, we can, okay, here the potential is minus v bar cos something, right?
Yes.
And then,
So the potential is minus v bar cosine of 2 pi over a r. Yes.
I think we can make it like a square wave.
Oh, okay. So you want to transform this, instead of a sinusoidal function, you want to transform it into a square potential.
Yeah, I mean, because it looks the same.
Yes, you could do that. I mean, nothing forced us to consider a sinusoidal function. Using a sinusoidal function will be very useful for the next calculation. If I could have used a square function, but a square function would have made my calculation, the next one, a bit more complex. While using the cosine, you'll see it in a moment that the result becomes, I mean, you can do it analytically in a very simple way. But yes, why not? You could use if you wish, a square potential here. It simply makes your calculation a little bit more difficult. This choice makes it much easier. Not for this calculation, because here you would have obtained 0 in an equally simple way with a square potential. But for the next one, you'll see that it makes a difference to have a cosine potential. Okay, so allow me now to go to the difficult part, this one here, where there is a degeneracy, because that's really the interesting point. So now I have to remember perturbation theory for degenerate states. I have to remember what to do. I need to consider the manifold of the degenerate states. And here I have two states, right? This is a degenerate manifold consisting of two degenerate states. I need to take those states and I need to calculate the expectation value of these two states with the perturbing potential, constructing the 2 by 2 matrix. First, 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 second, second, first, second, second of the two degenerate states. Okay? So first let me write down the two states. So the first one will be psi. They're actually both at pi over a. So they're both psi pi over a, right? K is pi over a. But there are two states. The first one is the one originating from the first parabola. So this one has g equals to 0, so e to the I g r 0, and it's e to the I k r, but k is now pi over a. So that's the first state. The states originating from the first parabola. The other state is the state that originates from the other parabola. Okay? Let's try to write it down properly. So the second state, oh, sorry, there's always 1 over square root of, obviously, right? Actually, we're in one dimension, so the volume of the unit cell is simply A, is the length of the segment. Second, 1 over square root of A, normalization. Well, e to the I g r. G is 2 pi, actually it's minus 2 pi over a, you remember, because the parabola centered at 2 pi over a is the one corresponding to minus 2 pi over a. So this is e to the minus I 2 pi over a r, and that's the periodic part of the block state. Then comes the block phase, but the block phase is the same as the other one because they correspond to the same point. Okay? Clear? So periodic part here is 1, here is the reciprocal lattice vector. The block part is the same because we are at the same k point. So obviously this is 1 over a e to the minus I pi I r. Okay, so it's very similar actually to psi 1. They differ only because of the minus sign, if I take all things together. Right. Then I have to carry out the 4 matrix elements. Let me do first the 1, 1 and the 2, 2. There's no difference between what we've done before. The only difference is that pi over a, k is now pi over a specific value. But when I take the expectation value of this with v, with the delta v, I'm going to get 0 because I already calculated it for a generic k, right? Psi, same psi, delta v, same psi. Whatever is k, that gave me 0. So it will be 0 also if k is equal to pi over a. So when I construct my matrix, and I'll do it here now, certainly I know that these two elements are going to be 0. These are the 1, 1 and the 2, 2 expectation values. I don't need to recalculate. If you wish, I redo it, but it's exactly the same calculation I did before for a generic k. The interesting part is the cross terms. So let me do psi 1 delta v psi 2. Integral from 0 to a, 1 over a, psi 1 minus I pi over a r. This is psi 1 conjugate because it's to the left. Potential cosine 2 pi over a r psi 2 e to the minus I pi over a r. I guess I need to use this portion of the blackboard because otherwise, to continue this. Now what I'm going to do is to decompose the cosine into exponentials. So I'm going to continue this and write it as 1 over a e to the, let me group the two exponentials, minus I 2 pi over a r. This is the product of this times this. Let me also put the minus v here in front. And then let me write the cosine as e to the I 2 pi over a r plus e to the minus I 2 pi over a r divided by 2. Okay? Now, this times this gives me 1. Of 1 divided by 2, right? There's a factor of 2. The second term is minus I 4 pi over a r over 2. But I'm integrating over a period a function which has the periodicity of a. Not only a, also 2a, by the way, but in particular also a. It is periodic with periodicity a. And it's a sinusoidal function. It's a, so the integral from 0 to a of this function, 0. Right? I'm integrating a plane wave over something which is actually twice its period. Its natural period would be 1/4 of 1/2 of a period. I'm integrating that over 2 periods, and so it's going to be obviously 0. It would have been 0 even if I integrated over from 0 to a over 2, but in particular from 0 over a. And the first part is just a over 2. It's a constant. Right? So the result of this is minus v bar over 2. Okay, minus v bar over 2 minus v bar over 2. So the 2 by 2 matrix that you need to diagonalize in order to obtain the eigenvalues after the perturbation is introduced within the degenerate manifold 2 by 2 manifold of the states which are degenerate here is given by this 2 by 2 matrix. Eigenvalues of this matrix? Plus or minus v over 2, absolute value, right? V bar over 2. Okay, so what used to be a degenerate manifold here is now split into 2 states, one at plus v bar. Well, v bar is positive, right? So I can just put v bar over 2 minus v bar. I don't need to care about the signs because I know that v bar is positive. One state goes up plus v bar over 2. The other state goes up, goes down, minus v bar over 2. So I split the degeneracy due to the perturbation. And whatever is the perturbation, even the smallest possible value splits the degeneracy because we are within a degenerate manifold. Now, what's going to happen now? We're going to discuss this in some detail in the next lecture, but let me just respond to what might be a question at this point. Well, we've noticed that states that are not degenerate remain exactly on top of the parabola. And I get to the edge, and suddenly there is a splitting. I mean, what's happening? Well, when we distinguish between degenerate and non-degenerate states, the distinction is not that clear, because if I have non-degenerate states which are extremely close to one another, that is, whose energy difference in the unperturbed case, I'm now thinking in terms of perturbation theory. Suppose you have two states which are not degenerate, but they're in the unperturbed Hamiltonian, but their distance in energy is much smaller than the perturbation that you're adding. Should you consider those two states are degenerate or non-degenerate in your perturbation theory, in your choice of your perturbation theory method? Degenerate, right? Because as long as these two states are close enough that they are below the splitting that you're going to apply, you need to consider them as degenerate. You need to solve the problem by considering them explicitly like we did here. So you see, as soon as we enter this region of K, we need to now introduce explicitly perturbation theory for degenerate states in order to deal with these states which are progressively closer and closer and closer to one another. As soon as this distance becomes less than V bar, we need to treat the system as in non-degenerate theory. So the bottom line is that we're not going to do the calculation, but the bottom line is that the final result looks something like that. Far away from the edge, no perturbation. Close to the edge, it smoothly goes to the numbers, to the two states that we just calculated for the exact point pi over A. And I think with this I'll conclude this lecture. Next time we will discuss in detail the results, the solutions. So keep that in mind, because next time we will discuss in quite some detail the actual shape of the wave functions, what is the meaning, and a number of consequences of this here. So today we have just derived the energies. Next time we're going to discuss the physics of this problem. So please try to come to class next time by trying to remember what we did in class today. Any questions? No. Fine. So Friday, no class. Okay? Because I'm on travel. So I'll see you again on Monday next week. The test will be presumably on Wednesday. Okay? So no test on Monday, because we only had two classes this week. So we're going to postpone the test to probably Wednesday or Friday next week. So see you on Monday.